Hello everyone, I am Professor Anish Vora and I welcome you all in this video lecture. In this video lecture, we will study about full adder, that is also one of the basic combinational logic circuit. First we understand the limitation of the half adder. In the previous lecture, we have studied about a half adder. For addition of two binary bit, we always use a half adder, but there is certain limitation of the half adder. For example, during addition of multi-bits, in case of previous carry, the carry from the previous stage, addition of 3 bits simultaneously is not possible in half adder. That is one of the major limitation of the half adder. In this condition, the better option is full adder. So now let us study a full adder. We start with a block diagram. The block diagram for the full adder, we have again two terminals at the input side, A as well as B. So we have addition of two binary bit, A and B. But at the same time, we have third input and that is known as a carry from the previous stage. In case of full adder, we have a possibility that simultaneously we can add 3 binary bits, A and B, as well as the carry from the previous stage. At the output side, again we have two terminals. One is a final sum, that is sum of A and B, as well as if we have carry from the previous stage, and we have carry that is known as a final carry, that is C out. Full adder is nothing but a combination of two half adder. We know the logic circuit implementation for the half adder, and if we combine two half adder, then we can prepare a full adder. Now let us understand the full adder with the two half adder. Again it is a block diagram for the full adder, but now it is with the two half adder. Suppose we have first half adder, we give input A as well as B, two binary bits for which we are planning to add each other. We have another half adder. Some output of first half adder that is given to the second half adder. We can see that some output of the first half adder which gives the addition or summation of A and B that is given to the second half adder, and carry from the previous stage that is also given to the second half adder. So some output of A and B as well as carry of previous stage will be added together in the second half adder. From the second half adder, we have final output that is known as the final sum or S. We have one OR operation, and at the input of the OR gate, we give output, carry output of the second half adder as well as carry output of the first half adder. In case of any carry generated either from the addition of A and B or from the addition of sum of A and B and previous carry. So in general, from the half adder 1 if we have a carry, or in half adder 2 if we have a carry, then with the OR operation we can have a final carry output, and that is C out. So with the help of two half adder, we can very easily understand the concept of full adder. Still, if we do the realization of the circuit in block diagram, again the concept or understanding will be much better. So now let us understand in different way. So we know that in case of half adder, the circuit realization is possible with one exclusive OR gate and one AND gate. So we have half adder 1, we have half adder 2. We give input A and B to the first half adder some output of half adder 1 that is given as a one of the input to the half adder 2, and if we have a previous carry, then the carry is given to the half adder 2 as a second input, and some output of half adder 2 that will be our final output as a S or sum. Again we have one OR operation. Carry output of first half adder as well as carry output of second half adder is given to the input of the OR gate. If any one of the carry is generated, then we will have a final carry, that is C out. So this way, with the realization of circuit, again it is a block diagram, we can easily understand the concept of full adder. Initially we discussed that full adder is nothing but a combination of two half adder, and that concept we can realize through this block diagram very easily. Now let us understand truth table for the full adder. We have inputs as well as outputs. In case of input, we have three input A, B and carry Ci. That carry is from the previous stage. And at the output side, we have final sum and final carry. We consider two input A and B. So we would like to add A and B, but at the same time, in case of previous carry also we would like to add with a summation of A and B. So what exactly we do to understand the truth table is, if we consider only two inputs A and B, then we have four different combinations of inputs are possible, that is 0 0, 0 1, 1 0 and 1 1. Now what we do is, with each condition we'll take a previous carry either 0 or 1. Now let us take first condition 0 0 and previous carry also considered as a 0. So sum and carry, final sum and final carry both are 0. Now with the same input 0 0, but we'll consider previous carry as a 1. So 0 0 input AB and previous carry we have considered 1. So sum is 1 and carry is 0, because 0 plus 1. So sum is 1 and carry is 0. Again we consider input condition 0 1. First with previous carry 0. So sum is 1, 0 plus 1 plus 0. Sum is 1 and carry is 0. We consider 0 1 condition with previous carry as a 1. So sum is 0, 1, 0 plus 1 plus 1. So 1 plus 1, 0 and we have carry 1. Now next condition is 1 0. First we consider with 0 previous carry. So sum is 1 and carry is 0. But now the same condition with previous carry as a 1. So 1 plus 0 plus 1. So sum is 0 and carry is 1. And the last condition, that is 1 1. First we consider with previous carry 0. So 1 1 0. So sum is 0 and carry is 1. And the same condition 1 1. Now we consider with previous carry as a 1. So 1 1 1. Sum is also 1 and carry is also 1, because 1 plus 1 plus 1. So sum is 1 and carry is 1. So we have a truth table. If we consider with the three inputs A, B and Ci, then we have total 8 different combination is possible. If we consider the equivalent decimal number, so it is a 0, 1, 2, 3, 4, 5, 6 and 7. And accordingly, we have sum. In certain condition, we have a high or one value in the sum output. And same way, in certain condition, we have carry generated, that is also 1. In the last condition, 1, 1, 1, we have sum as well as carry simultaneously, both are at high level. Before preparing K-map from the truth table, let us identify first for the sum and then for the carry the minterms, meaning is for which input combination we are getting high output. Let us see first for the sum. We have first input combination, and that is for 0, 0, 1. We are getting a high output in sum. So that is decimal number 1. Same way for the decimal number 2, that is 0, 1, 0 combination, we are getting 1. For 1, 0, 0, that is decimal number 4, we are getting again some high. And for the 1, 1, 1, that is decimal number 7, again we are getting high output in sum. So this way we can see that for the 4 different input condition or input combination, we are getting high output in sum. Same way we can identify for the carry also. So for the 0, 1, 1, that is decimal number 3, we are getting high in carry output. 1, 0, 1, that is decimal number 5, again we are getting high output in the carry. 1, 1, 0, that is decimal number 6, again we are getting high output in the carry. And at the last, for the 1, 1, 1, that is decimal number 7, again we are getting high output in the carry. So now once we have identified the minterms for the sum as well as for the carry, it is very easy to prepare K-map first for the sum and then for the carry. And from the K-map we can have easily simplified Boolean function. So now let us prepare K-map for the sum. Now in this condition we have 3 input combination. So we have to prepare a K-map with different 8 cells, that is 2 row and 4 column. We have our truth table for a ready reference. We have total 8 cell. We have taken AB variable on the horizontal plane. We write a number, that is 0, 0, 0, 1, 1, 0 and 1, 1. On the vertical plane, we take a variable Ci and we write a number, that is 0 and 1. Accordingly, we can write input literals, that is A bar, B bar, A bar, B, A, B bar and AB. Same way, Ci bar and Ci. If we write equivalent decimal number, then we can write 0, 1, 2, 3, 4, 5, 6 and 7. Now as per the truth table, we have to write 1 for each minterms where we are getting high output in the sum. So for the 1, 2, 4 and 7, we are getting high output. So we have written 1 in each cell. In remaining all other cells, we have to write 0. Now next task, that is to prepare a groups. But we can see that we have 4 different minterms, but pair is not possible, quad is also not possible. We will have to go for single isolated ones. So we have 4 different groups. And as per the groups, now we can write the product terms and finally the Boolean function in SOP form. So we write product terms. We have 4 different groups. So we can write a product terms, that is for the first group we can write A bar, B bar, Ci plus A bar, B Ci bar plus A B Ci plus A B bar Ci bar. So next task that will be to implement the logic circuit from the Boolean function. But before that, we'll prepare K-map for the carry also. So now let us prepare K-map for the carry. Again, we have truth table just for the reference. We have 3 different inputs, so 8 different cells. As usual, we are giving decimal numbers 0 to 7. Now again, for the carry also, we are getting min terms for 4 different input condition, and that is 3, 5, 6 and 7. So we have written 1 in each respective cells. In all other cells, we have to write 0. Now next task, that is to prepare the groups. We can see that quad is not possible, but we can go for pairs. So this first pair is possible. Then with the overlapping, we have second pair, and one vertical pair is also possible. So we have total 3 pairs. And if we write the product terms for each pair, and finally we write Boolean function for the carry in SOP form, so it becomes C is equal to B dot Ci for the first pair plus A dot Ci for the second horizontal pair, and for the vertical pair we can write A dot B. So now we have 2 Boolean function available in SOP form. We can easily implement a logic circuit with the basic gates. We have 3 different input, that is A, B and Ci. We use NOT gate to get A bar, B bar and Ci bar. So first, second and third, we use the 3 NOT gate and we get A bar, B bar and Ci bar. So now we have 3 input A, B and Ci, and we have 3 inverted inputs, that is A bar, B bar and Ci bar. Now as per our requirement as an input, we can use any one of it. Now first for the sum term, we know that we have total 4 product terms in the Boolean function of the sum. So we have 4 different AND gates. All AND gates are with the 3 inputs. As per the Boolean function, we have product terms, and in each product terms, we have 3 literals. So now we connect as per the Boolean function. Because Boolean function is in SOP form, at the end stage, we use a OR gate to add all the product terms. So we use OR gate. Now we have total 4 product terms. So we have used OR gate with total 4 inputs. Now output of each AND gate will connect as an input to the OR gate, and output of the OR gate, that is sum. So this way we have implemented a logic circuit for the sum with the basic gates. Same way we can prepare logic circuit for the carry also. As per the Boolean function of the carry, we have derived from the K-map. We know that we have 3 product terms. So we use 3 different AND gates. In each product term we have 2 literals. So as per the Boolean function, we give input, and as the Boolean function is in SOP form, at the end stage we have to use one OR gate. Because we have 3 product terms, so we have used OR gate with 3 inputs, and output of the AND gate will be connecting as an input to the OR gate, and output of the OR gate, that will be a final carry. So this way, with the help of basic gates, we can implement the logic circuit based on the Boolean function we have derived from the K-map. Also we can write our Boolean function, and that is S is equal to A B bar Ci bar plus A bar B Ci bar plus A bar B bar Ci plus A B Ci. That is exactly the similar Boolean function which we have prepared from the K-map. But now here we have a possibility. We can simplify this Boolean function. Suppose let us take a Ci bar common from the first two terms. So we have AB bar plus A bar B. Same way from the third and fourth term we can take a Ci common, and then we have A bar B bar plus AB. Now if we identify, we have exclusive OR gate, that is A B bar plus A bar B, and here we have exclusive NOR gate, that is A bar B bar plus AB. So we can write Ci, that is A exclusive OR B, A B bar plus A bar B, that is exclusive OR gate, and same way here we can write the Ci and exclusive NOR gate. Now for the A and exclusive OR gate B, we can put X. So we have written X for the A and exclusive OR B. So our equation S is equal to Ci bar X plus Ci X bar. Now as a whole, this Boolean function also indicates exclusive OR gate. So we can write S is equal to Ci exclusive OR X, and if we substitute the value of X again, then it becomes Ci exclusive OR A exclusive OR B. So the last equation we get, that is S is equal to A exclusive OR B exclusive OR Ci. The meaning is all the three inputs are connected with each other through the exclusive OR gate, and then output will get, that is our sum. Same way, if we write a Boolean function from the truth table for the carry also, then we have AB Ci bar plus AB bar Ci plus A bar B Ci plus AB Ci, and after simplification we get, that is C is equal to ACI plus BCI plus AB, and that is exactly equal which we have derived while preparing K-map. Now from the Boolean function of the carry, we can see that we have three product terms. So we require 3 AND gates and 1 OR gate. So ultimately, if we want to realize the circuit, we can use one exclusive OR gate with 3 inputs or 2 exclusive OR gate. We require 3 AND gates and 1 OR gate. So now again let us implement the logic circuit. We have used exclusive OR gate. We have 3 input, that is A, B and Ci, and output of the exclusive OR gate, that is sum. Same way we use 3 different AND gates for the carry. We give input connections as per the Boolean function. At the end stage we use one OR gate. We connect output of all the AND gates as an input to the OR gate, and output of the OR gate, that will be carry. So this way we can realize logic circuit with the help from the simplified Boolean function we have derived from the truth table. Now let us compare half adder and full adder. For the half adder, it can be used for the addition of 2 binary bits, while full adder we can use for the addition of multi-bits. If we check the hardware, in half adder we require one exclusive OR gate and one AND gate, while to prepare a full gate we require two exclusive OR gate, three AND gate and one OR gate. In case of half adder, output is addition of two signals, while in case of full adder, output is addition of three signals. Half adder is easy to prepare, while full adder is comparatively complicated. For the half adder, we have two input terminals and two output terminals, while in full adder, we have three input terminals and two output terminals. Half adder cannot be used as a full adder, but in case of full adder, we have a possibility that a full adder can be used as a half adder also. So thank you for watching my video. Keep watching. Thank you very much.